Good morning or good afternoon, everyone. Thank you for being with us today again, and welcome to the new Hypatia Colloquium. My name is Giacomo Beccari, and I'm very pleased to first of all congratulate with the speaker of today, and also to thank you for being with us today. And let me thank already since the beginning the two chairs of the session of today, which are Laura and Avinash, who are fellow and an ESO fellow and an ESO student, which they are with us, and they are super expert of galaxy formation and galaxy evolution. So we are very happy that they are going to help us and Cherry in the session. Very quickly, as usual, let me give you just few details, technical details. So people in some of the attendees are joining us directly in the Zoom meeting. In that case, you will be able to make a question yourself by using raise hand or by typing that you want to make a question on the chat, and then you will be given the word by the chair, so you can make the question yourself directly to the speaker. Or if you are watching the event on YouTube, in that case, you can use the live chat to make your question, and then the question will be passed to the speakers. Please be careful that there is, just consider that there is a 20-second delay between the time when you make your question and the time when we pass the question to the speaker. So at the live event, actually, not the pass it. So what else? So there is also another possibility. If you go to our web pages, so the Hypatia web pages, there you can also access the form that is available, where you can put your question and send it directly and press send. Then they will be sent by email, and then we are monitoring the email, and we will pass the question to the speakers, to the chair, and then from the chair to the speakers. Having said that, I think we are done. So just to remember that all the curriculum vitae and all the information about the speaker are available on our program pages. So if you go to the program page, you can click on the title of the talk, and then you are able to download the CV and access the information about the speaker in case you want to contact them afterwards. And also the videos we stay, of course, on the YouTube platform and are accessible via, if you subscribe to the channel, you can see there is a dedicated actually list of all the talks that are given this year, and but also there is the direct link also from the program page, so you can go there and you download the. So having said that, I think I can pass the word to Laura. And are you there? Yes.
Yes.
That was exactly. No, don't worry. So Laura, welcome. Thank you very much, and Avinash as well. And I see you later.
Okay, thank you, Giacomo, and good afternoon, everybody. I'm very happy to chair this new session of the Hypatia Colloquium together with Avinash. So let's start with our first speaker of today, who is Julia Victoria Seidel from the University of Geneva. Julia is currently finishing her PhD on the topic of exoplanet atmospheres, and today she will present part of her PhD work in her talk that is entitled Hotter Than Hell, Understanding Highly Irradiated Worlds Through Transmission Spectroscopy. So welcome, Julia, and when you're ready, you can start sharing your
Okay, can you see this?
Yes.
Give me just 1 second. I just want to minimize myself because looking at myself is always a little bit strange. All right. So thank you for having me. I'm very excited to talk to you today about exoplanets, especially since we're all now experts in galaxies and about redshifts and about supermassive stars. But this is the first exoplanet talk. And for those of you who don't follow the subject as closely as I do, you will probably hear here and there about an exoplanet detection, some outlandish claims about super Earth and such. So just to put that a little bit into context, as of now, we've found over 4,000 exoplanets. And there's so many by now that we can actually kind of start grouping them. So here you see the exoplanet population in the planetary radius versus insolation space. So that means that you have the radius of the planet on the y-axis, kind of Jupiter-sized planets at around 11 Earth radii. And then on the x-axis, you have how much irradiation, how much light do these exoplanets receive from their host stars compared to what we get on a normal day on Earth. And surprisingly enough, there is a population of absolute exoplanet superstars that we do not have in our solar system. They are highly irradiated, super hot Jupiter-sized planets that are called hot Jupiters. And these absolute superstars of the population, because they're so enigmatic, we have nothing like this comparable in our solar system, this is going to be the topic of today's talk, especially what we can learn about these very highly irradiated worlds through the means of transmission spectroscopy, and especially concerning their atmospheric dynamics. So what is happening to these atmospheres when they're blasted with the sandblaster of their star, basically. If you have some questions later on, you can also always hit me up on Twitter. So don't worry about thinking of something important to ask right now. All right, let's dive right into it. So what you see here is the most basic overview of transmission spectroscopy, because obviously I'm very envious of my colleagues in the planetary sciences because they can send probes and rovers and helicopters to their objects of study. And this is not something we can do with exoplanets. They are many hundreds of light years in most cases away from us. But what we can do is we can observe the host star, and the light that comes towards us from the host star towards the observer. For transiting planets, at some point the planet will cross between us, the observer, and the host star, and part of the starlight is blocked by the obscure planetary disk. So this is what you see in the lower plot here, that the flux of the star kind of goes down as a function of the phase of the orbit that we see. And this is, of course, proportional to the ratio of the disk of the planet to the disk of the star. So we can directly not only know, oh, there's an exoplanet, but we also know how big it is, and then infer something about what the planet likely looks like. Now, thankfully, we can do a little bit better than just inferring the radius, because so if you assume now that on the left you have your host star, and then we as the observer kind of on the right, and in between there's now this exoplanet that's on its orbit around its host star. And what you can see here kind of a little bit graphically depicted is the atmosphere. So you have different chemical components of this atmosphere. And since we are interested in the biggest ones, they're kind of like our Jupiter. So the main constituent of the atmosphere is helium and hydrogen. But there's also some trace metals in there. And for visualization purposes, I picked sodium. This is kind of the yellow dots here. Now, what happens when the light hits the atmosphere of this exoplanet while it travels from the host star to the observer? Well, pretty easy. Depending on the wavelength, some of it will get scattered, just with Rayleigh scattering. This is why our sky is blue, for example. And some will be absorbed by the constituents of the atmosphere. Now, depending which element it is, so for example, hydrogen makes up most of the atmosphere, so it gets absorbed over a very large portion of the atmosphere, so the planet will look a lot bigger. And for example, sodium that's not present up to the outermost layers will make it look also big, but not as big. So how can we find that out? Because, well, we just observe the starlight, right? And this is where spectroscopy comes into play, because just as Fraunhofer did back in the late 19th century, when he just used a prism to kind of split the light from our sun into all the wavelengths. And what did he see? He saw kind of distinct black lines where the light was absorbed and didn't reach us anymore. And for the sodium doublet, for example, this is kind of the famous one. It's called the Fraunhofer D doublet. It's kind of in the yellow range of the optical light. Now, thankfully, we have kind of come a long way from the prisms and the early spectroscopy of Fraunhofer. And now, instead of just having this binary of absorbed or not absorbed, we can actually resolve these two lines in the wavelength space. So meaning that we can really see at what height, what part of the light is absorbed in the atmosphere by these particles that are present. Now, I have been talking a lot about flux until now, but as you can see, the absorption of the light, so the flux that we get, is equivalent to where in the atmosphere the light was absorbed. So whether I talk about the relative flux or absorption, or whether I talk about height in the atmosphere, these are two completely interchangeable concepts. So keep that in mind for the rest of the talk. All right, that's enough technical details. We're now all up to date on how to do it. And what you see here is my sterilized assumption of what an atmosphere looks like. So on the very lower part of the slide, you have kind of the obscure disk of this Jupiter-like planet. And then I segregated the atmosphere into three regimes that I want to talk about today. So first you have the lower atmosphere. This is where all of human activity on Earth would happen, from the bar to the millibar level. Then you have kind of an intermediate atmosphere that reaches up to the thermosphere, where you have a lot of interaction with irradiation from the star, from the millibar to the nanobar level. And above that, the last layer is what we would colloquially call space, because this is where the atmosphere stops behaving like a liquid and you just have like random particles floating around. But this is actually a quite interesting realm, as you'll see in a little bit. Now, let's start with the lowest part. Counterintuitively, the lowest part of the atmosphere that is not obscure is actually quite well studied. And this you can do by not only observing the planet while it is in transit, this is what you see here in the upper right corner, but also during all the other phases of the transit, when reflected light from the star hits the surface of the planet, and we can still observe a little bit of light that way and see how this light interacts with the atmosphere. Now, this has the advantage that we can see different faces of the planet, so to say. We don't always just see kind of the orange slice of the transit itself. But of course, we get a lot less photons because we don't get the direct light, just the reflected light. And that means what people do is that they integrate over a certain wavelength band just to get more photons out of it. And if you do that in the wavelength band where different molecules are present, you obviously also get different absorptions and different behaviors depending on what molecule the light is interacting with. And this is what you see here on the right side for the hot Jupiter HD 189733b for the different observing bands. For example, the purple one would be carbon monoxide. All right, so we do this from space with the Hubble Space Telescope. We get these nice data points and then starts the modeling to find out what kind of model actually explains what we see in these observations. And this was done by Maria Steinrück in 2019 for the same planet. And she found something quite interesting. So she found that these shifts of the data, that you can reproduce all of this if you have a wind pattern in the very lowest part of the atmosphere at the 1 bar level. There's kind of a super rotational jet, so the material just gets rotated around the planet faster than the planet itself. That's something we also see, like, for example, for Venus, and also this banded structure that we all know quite well from Jupiter also works like that. But the moment you go a little bit higher in the atmosphere, around the millibar level and even like further below, you kind of get more of these cell-like structures, very wide structures as well. And I kind of tried to show this here as the white arrows, because what happens is basically that the planet is so close to its host star because it receives so much irradiation, right? That it, like our moon, it's tidally locked, and one side of the planet always receives irradiation, whereas the other side always looks out into space. Now, as a consequence, there is a large temperature gradient, and this drives a wind that upwells material on this very hot day side and transports it in a day to night side wind to the night side. And this is kind of the cell-like structure. So that means that in the lower atmosphere, we have these kind of zonal horizontal winds that go around the planet. That's already pretty interesting. Now, but that doesn't really answer the question yet, what does this atmosphere look like, right? So let's go to the outermost layer where we have absolutely only helium and hydrogen, basically, because they're very light particles and they can kind of penetrate the entire atmosphere. And if we now observe in transit, while the planet passes in front of the disk of the star, the absorption of hydrogen, then you kind of get these yellow data points here that I've shown from Bourrier et al. In 2013. And what his team did then is actually quite interesting, because they produced a fit to these data points. But if you look at this absorption signal in time, you would kind of expect that at the beginning and at the end of the transit that are marked here as these vertical lines, you would have no absorption. All the absorption happens while the planet is in view, so to say. But what you see here is that at the beginning you have very little, and then it kind of peaks asymmetrically, and you have this long tail of absorption while the planet is already gone, like it shouldn't be there. And the way that I explain it is kind of seen in the lower panel, so that these ultra hot planets receive such a blast from the star, so much energy, that it creates kind of a comet-like tail. So you have this bow shock in the front where the irradiation hits, and then it drags this cloud of material, of hydrogen behind it. And well, that's not entirely surprising. So we can estimate the mass loss rate. Part of the atmosphere gets blasted into space. But how are these two connected now? Like we have these zonal winds like from Jupiter in the lower atmosphere, and now we have this outblasting in the outer atmosphere. How can these two possibly be connected from an observational point of view? Can we put any restriction on this so that theorists can work with that? And this is where the sodium doublet that I already hinted on comes to the rescue. So what you see here is the sodium doublet again for the hot Jupiter, HD 189733b. And not only can you see that it absorbs really high in the atmosphere, though it really probes this intermediate atmosphere that I was talking about, but also that now we can produce like theoretical absorption models and kind of try to fit this sodium line at different altitudes and see what that means. Kind of in a Frankenstein approach, just like slicing this data into bits in height. This is what they did. And in Wittenbach et al. 2015, they were able to really produce a temperature gradient from the different broadening in height for the sodium doublet. Now that's nice, but one of the things they immediately realized is that just with thermal broadening of the sodium doublet, you can't explain the line shape that we see correctly. And this is when my PhD started, because you can use this theoretical forward model that is widely available, and you can say, okay, what happens if I also add atmospheric winds? And just as we know from high school physics, we use Doppler shifts to see how this wind interacts with the light. So instead of just having the forward model and modeling the temperature, we now also add winds and where do we set the continuum and a lot of other parameters that I don't want to get into too much detail. But I only have 4 years for this PhD, so I can't redo this model for all the different permutations. So I combine this with a multi-nested sampling retrieval, so the computer can tell me not only which values for the parameters give me the best fit to the data, but also which model is the best fit. And so far, everything that I've shown you is based on data taken with a Hubble spectrograph at the 3.6 meter telescope in La Silla. And a very interesting survey came from this instrument that was led by David Ehrenreich. There's a few papers here if you're interested in this transit spectroscopy. But one of the things that this survey was intended to do was to scan a lot of interesting exoplanets and find which ones are best to observe with the big sibling of Hobbes, espresso, at the VLT. Now, this is my favorite plot, because this is the ultra-hot Jupiter WASP 76b, and you see again the sodium doublet in absorption, but you see it for different instruments. So in the upper panel, you have HARPS, and then in the middle panels, you have 2 transits each for espresso. And the first moment I saw these espresso datasets in Tabanero et al. 2020, my first thought was, I need to get my hand on this amazing data. So I did, and I combined these 3 datasets into one, and I unleashed my retrieval model on it to see whether I can restrict the wind speeds from the sodium doublet. And long story short, I could. And what you see here is in height, the sodium doublet of WASP 76b again, but you also see the best fit model. And of course, it's striking that the fit is extremely good, but you can also see that it correctly models not only the offset of the center of the line from where we would expect them, but also kind of this asymmetric line shape that there is in the red arm, kind of like a bumpy feature. So what does that mean? All right, this is the posterior distribution of the parameters. Ignore the two ones that are kind of grayed out here. I don't want to talk about that today, but you can really see that the two velocities, the wind speeds that were retrieved, are really precise. And what the computer basically told me is like, okay, for the lower atmosphere, of all the different possible wind patterns in this universe that you gave me, up to the millibar level, a day to night side wind of kind of 5 kilometers per second is best, which fits nicely with what we already know from theory. And then for this intermediate atmosphere, I need a vertical wind of around 22 kilometers per second. That is huge. It's still below the escape velocity to blast it off into space, but it's a huge, huge wind speed that can now transport this material to the exosphere, to this outermost layer, and also fuel the mass loss that we saw from the observations of hydrogen. And this is super interesting because now we know that there's like this vertical wind structure in the intermediate atmosphere that now is a theoretic, like a observational constraint for theoretical studies of what happens in these outrageously hot worlds. And obviously observations are only good if they can be reproduced. So what you see here is again for WASP-76b, but this time it's iron and not sodium. So you see here the iron detection kind of in time. So you start at 0, and then you see this yellow trail of the sodium that kind of veers off to 10 kilometers per second as the transit progresses. Now, here you can just have to believe me a little bit, but the thing that they found out is that this iron kind of is stationary at the beginning of the transit and then is at kind of 10 kilometers per second. And if you now, we know how fast this planet rotates, it's 5 kilometers per second. So if you now add a 5 kilometer day to night side wind, that means at the beginning, the two wind speeds would be kind of in opposite directions, canceling each other out. We're at 0. And then on the other half of the planet, on the other terminator where the light comes towards us, the two would be parallel to each other and combine to this 10 kilometer per second offset. So this, a different observational technique, gets exactly the same result as I get from an actual retrieval algorithm. And this is very encouraging that we now have observational constraints to learn something about atmospheric dynamics, especially under very extreme circumstances. So with that, I just want to leave you with the conclusions, a little summary, and leave you with a teaser, because when I start my first postdoc at the end of the year, I'm going to see how I can use this technique to learn something about smaller and cooler planets, because obviously the holy grail of our field is to find a planet and characterize a planet that is more Earth-like. Thank you very much.
Thank you, Julia, for this very, very nice presentation and for the nice work you've done. Before we wait until someone has any question, I want to start. This is a very naive question because this is very far from my expertise. So I was wondering, I guess, that when you retrieve your spectroscopic data, you like combine all the effects for all the atmosphere, no? You can't disentangle what is the lower level or what is the higher one, right?
Yeah, this is actually where this retrieval approach comes in so handy, because imagine it, like we see this planet only in transit, right? So everything that is kind of on this limb, we'll see combined, integrated over. But with the retrieval, I can say, okay, I'll just float the boundary between the different layers, and computer, please tell me from the data, do I even need two different realms? Can it be the same wind pattern? And if there is a distinction between the two, where do I set it? Because the sodium line still comes from these different levels of height. So if you're like in the lower realm, there's everything combined, and then in the upper edge, so to say, you really only get the influence from the more upper layers of the atmosphere. But yeah, this is why I'm really happy about every new spectrograph that comes online at ESO, because the better the precision of the spectrograph and the bigger the mirror, the more precise the data and the better this distinction works. This is why my first work on HD189, where I also tried this, it was more vague. I could only put like upper limits because the HARPS data didn't allow me to do more than that.
Okay, thank you for answering the question. And another naive question is, why do you use sodium? Is there a reason why?
Yeah, so sodium is a resonant line, meaning that the sodium doublet, we only need like a trace amount of sodium to get a really strong absorption signal. You could also use, for example, if it's detected potassium or lithium or calcium plus, like there's a range of lines, but you just need this resolved line shape basically. And then however deep the line is, this is the height in the atmosphere that you can probe. But sodium so far for these ultra hot planets, we have just detected it very often and very strongly. This is why it's very handy.
Okay, thank you. Does someone else have a question for Julia? Please don't be shy and ask her. Yeah. Avinash, do you see any question in the chat of the YouTube?
No, not at the moment.
Well, I see a question from, Giacomo.
Yes, sorry. Yeah, thank you very much. Actually, Julia, thank you. Really, really fascinating talk, and very, very, very nice also to see, to watch, and easy to really. I'm not from the topic, so I could follow very well. So thank you very much.
I'm glad.
Yeah, thank you very much, really. But my question would be, I'm just out of curiosity, really, looking at your conclusions, the fact that you mentioned one of the conclusion. I'm reading because I have the YouTube chat. I pause it on the chat on this slide just to look a bit more. So you say that you see hot Jupiters evaporate material beyond the Rob Losh, right? So I was wondering, do you have other observational evidence to see this event?
So we've seen this surprisingly, we've seen this for some hot Jupiters, but not all of them. We've seen it for some ultra hot Jupiters, but also not all of them. And the question why is still a little bit outstanding, because I mean, obviously it's an interplay between the irradiation from the host star and the gravity of the planet hanging on to its atmosphere. But there's also more to it. For example, interactions between the ions in the atmosphere, because there's a lot of ionized materials simply because of the heat, and the magnetic field of it. But magnetic field measurements of exoplanets are hard. And so far, we have done this for HD189, for example, in Colley et al. 2019, and that is basically the first work where that was kind of estimated that these hot Jupiters have magnetic fields about 50 times higher than our Jupiter, which is crazy.
Wow.
And so if you have ionized sodium, like in the outer thermosphere, for example, that could easily just travel with the magnetic field and like that move beyond the Roche lobe. There's also a few little bit more outlandish theories out there about material coming from the moons and stuff like that, but I don't want to get into that today.
Okay, I see. Okay, thank you very much. I see there is a question from on the chat, so I maybe pass it, but right. Thank you, really, congratulations.
Okay, thank you, Giacomo, for the question. And yeah, we have a question from Linda in the chat of YouTube. Yes, Julia, can you resolve the layers during ingress or egress? Because the outer layers obscure the star first when entering? Yeah,
I'm really hoping I can. So far, that wasn't possible yet. I tried for WASP-76b, for example, because we do have espresso data, but because I didn't want to discard the HARPS data, simply because I don't think it's good to just use your favorite data set and discarding, biasing yourself by discarding the rest of the data. But I recently obtained 3 transit with espresso on a different target that I'm not going to tell you about. And I really, really hope I'll be able to do that. I got enough transits to have the signal to noise to like really resolve the sodium doublet for ingress, for egress, and also hopefully see, because the planet is turning kind of 30 degrees while it's in transit from one side to the other, to really be able to see that extra bit of atmosphere that I get on the edges. That would be super cool.
Good. So I guess that you will let us know when you have that.
We talk about that next year.
Yeah, okay, great. Well, I think that I'm going to ask you another question because I was curious about, you said that this spectroscopic technique you apply to hot Jupiter exoplanets, but can it be applied to other kind of, like to planets that are farther?
Yeah, so the thing is that hot Jupiters are easy, because first of all, we bias ourselves towards finding them because they're large, and because they're very hot, they are not encumbered by clouds, for example. There's no clouds, it's too hot. And you have most of the molecules dissociated into atoms. So you get like really these nice spectral lines and not more molecular bands. That makes things easy. So at the moment, the field is still very young. I mean, the first exoplanet was found 25 years ago, the first atmosphere, not even 20. And so we're kind of trying out all of these techniques now on these ultra hot Jupiters and with better telescopes. So my plan is to push this towards Neptune-sized planets and also towards cooler planets, but it's a iterative process to kind of get there depending on the techniques and also obviously on the telescopes that we have. But yeah, there's plenty of observations already of sodium doublets on Neptune-sized planets, and kind of trying this out on this class of planets is on my agenda.
Okay. So you have a lot of work ahead.
There's lots of work to do. Thankfully, I already snatched the job for the next 4 years, so it will get done.
Great. So okay. So I think that we are out of time. So thank you again, Julia, for this.
Thank you so much for having me. It was a real pleasure.
Yeah, very nice presentation, and good luck with your next steps. So now I leave the floor to Avinash and to the second speaker of today. Thank you.
Thanks, Laura. Hello and good afternoon, and my greetings to everyone as per the time zone. Many thanks, Julia, for a very nice talk. Now let's move on to our next speaker. I'm very happy to invite Martin Ray, who is currently a postdoctoral research fellow at the Lund University in Sweden. Martin will be talking about the diversity of the dwarf galaxies. His talk title today is From Quenching to the Gas Reach to the Star Forming, the Diversity of the faint dwarf galaxies. Just a quick introduction about him. Martin did his PhD in astrophysics from University College London, and he holds 2 masters, one in aerospace engineering and in physics. And his research interests are in the formation and evolution of galaxies, dwarf galaxies, and cosmological structure formation. So now let's hear Martin talking about the dwarf galaxies. Please go ahead.
Thank you very much, Avinash. So hopefully you can see my screen.
Yes.
And I will start. And okay, so hello everyone. Thank you very much for this introduction. So today I wanted to present to you some of the work that we've been doing on modeling the diversity of faint dwarf galaxies. And the reason we became very interested in faint dwarf galaxies is because there are 2 really big open questions in astrophysics that we are yet to pinpoint. One is the first one is the nature of dark matter. We know that dark matter is out there in our universe, but we are really yet to pinpoint its astroparticle nature. And the second is how star formation is regulated in galaxies. We can observe the fact that massive stars exploding massive stars and the ionizing radiation from massive stars regulates star formation, but we are yet to really understand how these processes regulate the interstellar medium and drive outflows, for example. And the good news is that if you care about these two aspects, lower mass galaxies are increasingly sensitive to both, in the sense that lower mass galaxies inhabit the lowest mass dark matter halos and are the most dark matter dominated, so they are increasingly sensitive to the nature of dark matter. And because they live in such shallow potential well in such small dark matter halos, any explosion that goes within them has triple the impact than in something like the Milky Way. So by going faint and by targeting the lower mass galaxies, we really aim to pinpoint and to put constraint on both of these aspects. And the further good news is that there's been an observational revolution about faint dwarf galaxies. So what I'm showing you here is the population of faint dwarf that we knew until 2005 as a function of their V-band magnitude, so their stellar content on the y-axis, and their stellar sizes on the x-axis. And the reason I picked 2005 as a limit is because in 2005, SDSS happened, and it was one of the first wide field deep survey in astronomy, and it discovered many new dwarfs. We nearly doubled the amount of dwarf that we knew if I let the years of SDSS pass by. And actually, if I further allow time to pass and put the DES and PenSTARRS photometric surveys on there, you see that we keep populating the bottom part of this plot right here. And there's basically two trends that I really want you to focus on this, is that as experiments improved over the years, we keep discovering fainter and fainter dwarfs around the Milky Way. But there's also a more subtle trend, which is at a given total magnitude, we also keep discovering larger dwarf, and that's a surface brightness argument. If you have the same stellar content, but it's spread out in a larger size, you are effectively a lower surface brightness object. And actually, this is really telling to me, because this line here is a line of constant surface brightness. So you can see that the slope of it is almost matching the slope of the observation. So to me, this is saying that the observations are probably surface brightness limited, and they are huge prospects to discover even more faint dwarf galaxies and lower surface brightness dwarf galaxies with upcoming telescopes like Vera Ruby or the Nancy Roman. And actually, I can cheat my way a little bit into this argument by adding two more points, which are detections from 2019 and 2020 in Gaia and Hyper Supreme Cam. And you see this trend going again. The fact that this bottom right corner is probably not everything. There is probably some galaxies in this bottom right corner, and that we haven't yet fully uncovered the full population of faint dwarfs. Okay, so what we really want to do with this large amount of observational data is to turn it around and to use it to constrain dark matter and galaxy formation. That's a really hard problem, unfortunately, because in order to model a population, we need to model multiple objects with multiple environment and multiple histories, cosmological histories, while resolving the feedback processes that goes on within their interstellar medium. And I want to stress that these dwarf galaxies, they are extremely tiny. Their sizes are 100 parsecs. So this creates an extremely large dynamic range problem, making numerical studies of galaxy formation very challenging. And so today, what I wanted to showcase to you is how we've come, is a project that we've developed, the EDGE project in collaboration between Lund University with Oscar Aggert's, Surrey University with Matthew Orkney and Justin Reed, and University College London, where I did my PhD with Andrew Ponson, to tackle this dynamic range problem and to improve the modeling of faint dwarf galaxies, and in particular of their diversity. So the way we've been approaching this problem is by using what we call cosmological zoom simulations. So the idea is that we start from a cosmological object. So this is the top left panel that you see here. It's a cosmological initial condition. And we concentrate our resolution and numerical effort within the black region in the center. And within that region, we are actually able to reach very high resolution of about a parsec size. And this is, I want to stress that this simulation, a parsec size is not just an incremental change in resolution. It's actually a very physical scale, because it allows us to resolve the explosions of individual supernovae within the interstellar medium of the dwarf. And that takes out a lot of the uncertainties that typically plague cosmological simulations of galaxy formation when it comes to modeling feedback. So I won't go into the details of the simulations. I'll just say that they are hydrodynamical simulation. There's a very extensive galaxy formation model with feedback from massive stars in general and from late time stars too. I'd be happy to answer any questions. Otherwise, it's summarized in this paper that was led by Oscar Agertz last year, sorry. Because today I want to focus on the results, and I want to show you what the ultra-thing that we simulate look like. So this is a movie from one of our first simulations, and the first thing I want you to note is the cosmological environment. You see, we are now looking very early on in the age of the universe, and you see these filamentary structures of gas that feed the galaxy. This is what a cosmological zoom simulation gives you. And if I let the movie run forward, you see this explosion going off, which come from a modeling of stellar feedback and supernova feedback in particular. Now, if I let the movie run forward again, you'll see that these filamentary structures I was pointing out is starting to disappear. And actually, if we go even further, you'll see that the entirety of the screen turns black. The entirety of the gas has disappeared from the movie. And that's the effect of cosmic reionization. So when reionization kicks in around redshift 6, it heats up the universe, it heats up the intergalactic medium and introduces a thermal pressure floor in the gas surrounding these galaxies, and this thermal pressure prevents the gas from clumping on the very small scales of the galaxies that we're looking here. So actually, it's not that the gas has disappeared from the movie, it's just that it has become so low density that it's turned black in this color scale. And it's not the end of the life of the galaxy. If we switch back to the same galaxy in dark matter, you see that the host halo is actually very active. There's a lot of things going on. It's undergoing merger and accretion and so on. And we'll come back to that, but basically my basic point is that after reionization, these galaxies are not allowed to form stars, and they've lost almost the entirety of their gas. And to put this a bit more quantitatively, if we look at the plot of the halo mass as a function of time and the star formation rate in the bottom, you see that when reionization actually when the universe becomes reionized, there are no star formation spikes after redshift 5 or 4. And that leads to an extremely low mass galaxy of about 10 to the 5 solar mass. I want to just take a moment, because most people, when they look at galaxies, are not super used to talking about 10 to the 4 or 10 to the 5 stellar masses. But here, this is really the ultra-faint range. And the point is that you end up with very low mass star for. Okay, so on if we want to go back to these starting questions and say what have we learned about dark matter and galaxy formation from this, we are still really far away from quantifying a population. We are still really far away from understanding how different environments and different histories affect the properties of this galaxy that we just simulated. And actually, this is where the second aspect of the EDGE project comes in. And it's using what we call the genetic modification technique. And the idea of it is to take the galaxy we just started with its cosmological initial condition on the left, and actually generate a new initial condition for it that is the point, and it's now on the right. And the point is that it's almost exactly the same. And visually, it's very hard to see the difference. But if I show you the difference, you see that I've made some tweaks to the early universe density field. And I won't go in the details of how we do this tweak. It's what a technique I developed over my PhD. But what you need to know is that this technique engineers the initial condition in order to achieve targeted specific changes to the late time accretion. And when we evolve this new initial condition forward, we get this new movie on the right. And again, the basic point is that this is almost exactly the same galaxy. You see the same filamentary structure. But if I let the movie run forward, you might have the feeling that the one on the right is a delayed version of the one on the left. And that's actually exactly what I've done. Using genetic modification, I have engineered the initial condition of this galaxy to actually make it grow slower before reionization and then allow it to catch up later. And actually, the strength of this technique is that we can actually push this even further. We can make a galaxy that grows even slower, or actually turn the problem around and make a galaxy that grows even quicker, all converging to the same final halo mass. And then we can compare how these different histories for an ultra-faint lead to difference in the observable. And this is the stellar mass on the right. And you see straight away a very systematic effect that earlier forming ultra-faints have systematically higher stellar masses at fixed halo mass today. So if you're wondering what these steps after reionization are in the green galaxy, these are actually late accretion events, which are not star formation, and we'll come back to those in a minute. Because for now, what I really want to stress is the fact that this is all happening at fixed halo mass today. So actually using this technique, we are in prime position to predict the scatter that is expected in the stellar mass to halo mass due to the diversity of possible histories for dwarf galaxies. And actually we can show that it leads to a 1-deck spread in the stellar masses of these dwarf galaxies. So I said I wanted to come back to these dry mergers, and that's because the stellar mass is not the only observable that is affected. So if I show you a picture of the purple galaxy, you see that it's quite a dense nugget of dwarf galaxy. But if I show you a picture of the green galaxy, it's actually this very diffuse with really big lobe dwarf galaxy, and that's because most of its stellar mass is actually accreted through these late mergers, and these mergers deposit their stars on very elongated orbits, inflating its size. So when we put back this galaxy on and compare them to observations, what we find is that 3 of them actually cut through the observational cloud, which is very nice, knowing that the observations are probably probing through different histories. But this green galaxy is in this bottom right corner I was mentioning at the beginning. So we actually are in a position where we can say there should be galaxy out there. We can predict that there should be galaxies out there, not because we are surface brightness limited, but because we expect them from the diversity of possible history available in a lambda CDM universe. Okay, so in the last few minutes of the talk, I actually want to focus on a slightly different source of diversity. And that's because I haven't really mentioned this before, but one point on this plot is actually very special. And that's this one that I'm highlighting right here. That's Leo T. And Leo T is special because it's actually star forming. It is not a quenched dwarf. It's a picture, here's a picture of it on the left, and you can see blue stars. And you can also see this H1 contour. So it's detected in H1 and it's star forming. And and actually in recent years, in the last five or so years, there's been a number of other faint dwarfs that have been detected through their H1 content with very low levels of star formation. And they actually overlap with the faint and ultra faint range that are all quenched galaxies. So we really want to understand what is the source of this diversity, what actually makes this faint dwarf star forming or quenched. And in order to do that, I'm going to use a more extended suite of simulation from the same project. So the blue galaxy is the same one that we were showing, that we were looking at before. And you can see that it's quenched after reionization. It's got no late time star formation. And then I'm going to introduce this red galaxy right here. And actually, when we started looking through our results, we became very excited because we realized really quickly that this red galaxy, it also forms stars before reionization, and then something happens. And then it's allowed to reignite star formation at late times. You see all these spikes of star formation at late times. And we end up with two objects with extremely similar stellar masses, but one of them is star forming at an average rate that is extremely close to what is observed in Leo-T, Leo-P, and in this faint dwarfs. So we wanted, so the most obvious difference between these two objects is their late mass buildup, right? The red galaxy actually is hosted in a 3 times bigger halo mass. So we wanted to understand whether this late mass buildup, it was actually the reason to enable the rejuvenation of star formation. And in order to do that, I'm going to introduce, we were lucky enough to have another object that sits exactly in between these two, and that's this yellow curve here. And you can see that this yellow curve doesn't actually show late time star formation. But using the genetic modification technique, what we can do to test this hypothesis is actually to generate yet another initial condition that we engineer such that its halo mass is larger at late times. And that's this olive curve right here. You can see that it achieves a higher halo mass at late time. And if we look at its star formation history, we can see that it also reignites star formation. So with this, we can demonstrate that increasing a galaxy's dynamical mass allows it to reignite star formation. We also, when we were doing these numerical experiments, we also found something else, which I'm going to flash because I don't have so much time to talk about it. It's that the dynamical mass was not the only thing that played a role in allowing these galaxies to rejuvenate and reignite star formation or not. And actually, because these galaxies are so small and so sensitive, any source of feedback, even from massive stars like type 1a explosions or wind from AGB, can actually prevent gas from cooling and prevent star formation within the interstellar medium. And we found that if we artificially remove these sources of feedback from our simulations, we could also force the reignition of star formation at late time. So in the last part of the last part of the talk, I actually want to emphasize once more the diversity problem and the diversity that we're able to highlight with this kinds of approach. So here is all the galaxies that you've seen today from the Edge suite. The 4 galaxies that we saw at the beginning that are all quenched by reionization with no late time star formation. The galaxy that shows signs of star formation, and this yellow galaxies which is about to start star formation but hasn't quite made it. And if you focus really in the middle of the plot right here, you can see that at almost identical stellar masses, we actually find an example of a galaxy that is fully quenched, no gas, no H1 content. Another galaxy that is star forming and is detectable in H1, and another galaxy that has exclusively all stars but an H1 content. All of that at similar stellar masses. And so that brings me to my conclusion. So I hope I've convinced you that genetic modification allows us to construct controlled studies and to establish a causal account between a dwarf galaxy's history and its observables. By using it on cosmological simulations of ultrafaints, we can show that earlier forming ultrafaints have systematically higher stellar masses, directly probing the expected scatter of stellar masses at fixed halo mass. We can also highlight a new formation scenario predicting the existence of highly diffuse and extended ultrafaints to be discovered by future photometric surveys like Vera Rubin. I've also shown you how a late growth in dynamical mass can lead to the reaccretion of gas and late type star formation, very similar to Leo-T and Leo-P, and how this drives strong diversity in not just stellar masses and sizes, but also in stellar ages and H1 content in these galaxies. And I'll leave you with my summary and take any questions you might have.
Many thanks, Martin, for this wonderful talk, and thank you for introducing something new, genetic modification, to the astrophysics world. So are there questions for Martin? Please go ahead. Okay, yes.
Something new.
I see two people have raised hands. Maria?
Hi. Sorry, I have a baby, so it's a little loud here, but hopefully you can hear me. I have a lot of questions. I'm trying to understand basically, how do you actually get a faint dwarf? Is it always a faint dwarf, from the beginning of its lifetime? So when you model, how do you think about it? And another question was, do you know what percentage is the dark matter in different types of dwarfs that you looked at?
So they are not always faint. So before reionization, they are normal low mass galaxies. The idea is that reionization completely shuts down their later star formation. So they are not allowed to grow after that, after redshift 4, which is very early on in the age of the universe. And so because they are hampered from the very beginning of the universe, they become extremely dark matter dominated. So for example, so to answer your second question, the stellar masses of this dwarf are about 10 to the 5. They have no gas, and they live in dark matter halos in all cases of about 10 to the 9. So the ratio between the two is 10 to the -4. So they are 0.01% baryon. They're 0.01% baryon in them.
Yeah, thank you. I guess I wasn't sure how to picture then some dwarfs that have been recently, I read some papers, not a lot of them, but they are compact galaxies, but are bright. So how, if you know, how do those come about? How is it that their star formation is not quenched during the reionization?
So I think the compact galaxies that you're mentioning, they tend to be within dense environments. So like more like cluster or group environments, I think. In this case, what we are looking at here are isolated dwarfs. And in the case of the compact objects, you can imagine star formation being triggered by gas compression during interaction, for example, or to reduce sizes due to tidal stripping.
Thank you very much.
Pleasure.
Thank you, Martin, for answering the question. Now there's a question from Anna.
Hello. I had a question about how is reionization actually modeled in EDGE? Do you expect your results to change depending on the redshift of reionization and implementation and so on? And maybe I have a follow-up question based on your response.
So the modeling of reionization is the standard UV background. So reionization is a global process across the universe, which in all cases where we focus on single objects, we have to make approximations for it. And the way we model it is a homogeneous time-dependent UV background, as is usually done in cosmological simulations. Actually, if we, in this paper right here, we actually looked at varying the redshift of reionization. And what this did is it quenches star formation earlier or later, depending if reionization is earlier or later. But it never actually prevents, for example, late-time star formation. So it definitely plays a role in setting the structural properties of this dwarf. And it's something that we've only begun to quantify.
I think, so you would expect, would you expect higher stellar masses for the ultrafaints if you have reionization happening later, or what is this?
So yes, but the way I usually think about it is more about environment, because reionization happens at different times in different environments. So if you're in a really dense super like protocluster, for example, you will reionize very early because you have a very big overdensities of galaxy. Whereas if you're in a cosmic void, you will reionize late. So what you should see is more of a modulation of the ultra-faint stellar masses with a cosmic environment, which you can then map onto a late versus early reionization argument. If you send me an email, I can point you to papers quantifying this if you want.
Okay, thank you.
Martin, you have a question from YouTube chat from RS. Has there been any effort in studying the, in bracket, most likely low molecular gas content in these simulated dwarf galaxies? Maybe through post-processing? Is that something that would be feasible?
So that's an excellent question, and that actually is something that is in preparation. So we are looking at how detectable the molecular gas in the star-forming dwarfs can be, and in particular whether it could be detected with ALMA. So I don't have an answer just yet, but we are quantifying both the H1 observability and the H2 observability of these dwarfs.
Thank you, Martin. Maria, do you have a question? I see still your hand is raised. No, I don't think it's a question. So if there is there any other question from someone? Yeah, Pavel?
Hello. I was wondering, have you considered the morphology distance relation? So the fact that dwarf galaxies, low mass dwarf galaxies beyond about 200 kiloparsecs are happily star forming, and the planes of satellites, the fact that these satellite galaxies are typically in planes, how your understanding might be affected by these observational findings?
So the entirety of the simulation work I've shown here is performed for isolated dwarfs. So we do not actually, in order to achieve the dynamic range that we achieve, we cannot model the Milky Way, for example, or a Milky Way-like environment. So we haven't looked at so this is something we plan to do as a follow-up of all these results, and is to try to quantify how these findings propagate in a Milky Way environment. And we plan on doing this with both numerical simulations and more semi-empirical models. And then we haven't really thought about the planes of satellites, to be honest, but I think it would be interesting to look at it too.
Okay, thanks.
No problem.
So there are thanks to both of you, Martin and Julia, from the YouTube chat.
Well, thank you back.
If there are no further questions, let's go to Jack.
I have a question.
Yeah.
Maybe you mentioned, I missed it. So at this dwarf galaxies, you mentioned getting feedback from stellar processes, but how about any sort of black hole activity? Is it completely ruled out? I actually don't know. Thanks.
So that's a very good question, to which there isn't a single answer. So for a very long time, it was believed that stellar feedback was the main source of feedback within these dwarfs. There is growing observational evidence of AGN activity in dwarfs. How much these AGNs matter and how much of their energy couples to the gas, I think is still under debate. So none of the work we have here includes AGN feedback, but I think this is definitely something to keep an eye on in the future.
Thank you, Martin, again for answering the question. And Giacomo.
Yes, so thank you, Avinash. So first I would like to, so we can conclude that the seminar of today. So thanks to the participants for being with us. And I would like to sincerely congratulate Martin and Julia for the excellent quality of the science that they are doing and the very, very, very clear presentation. So congratulations, and I hope to see you in real time very soon around it, and the same for everyone. And also finally my thank to Avinash and Laura for chairing the so well and so perfectly actually the event. So I like really just to say that the nice atmosphere that you chairs are triggering in these events is really great for us, and is exactly in the spirit of ESO way to see science and a nice scientific environment. So thank you very much for making that happening. So to everyone, see you next week. We will have another event of the Hypatia, and then we will have toward the end of the month we have the ESO Cosmic Duologue, and it will be about the formation of the bulge. So that will be also a nice event. With this, we can close and see you soon then.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye.